Gross-Pedayevsky picture. Namely, on the one hand, the size here of the balls stands for the relative size of the contact interaction, and the relative size here of the error depicts the strength of the dipolar interaction. And when we go here from this to this picture, you see that the dipolar strength increases relative to the contact interaction. And what one observes is that the Bose-Einstein condensate is elongated along the dipolar interaction in order to minimize the total energy. And I would like to add to this mean field Gross-Pedayevsky picture an analysis which asks how this picture is modified by taking into account additional quantum fluctuations. And it will turn out that this tendency to become elongated along the dipolar direction is diminished by taking into account quantum fluctuations. Let me first of all introduce the systems one is dealing with. There are two main origins for dipolar interaction. The first one are magnetic atomic systems, where one has a magnetic dipole-dipole interaction, which is given by the square of the magnetic dipole moment, where the dipole moment may range from 1 up to 10 Bohr magneton, if one considers the different isotopes in the periodic table. Most prominently, there's the chromium-52 realized in 2005 in the group of Tillmann-Pfau in Stuttgart. And just last year, dysprosium was realized as a BEC. And just a few days after Easter, also the condensation of erbium was reported. For chromium, the magnetic dipole moment is 6 Bohr magneton, for dysprosium 10 Bohr magneton, and for erbium 7 Bohr magneton. And you have always to take into account that the square enters, which means for dysprosium, the dipole-dipole interaction strength is 100 times larger than for the alkali metal BCs. Now, if we look for electric dipole-dipole interactions, they occur once one has realized heteronuclear molecules in the Rho vibrational ground state. This was achieved in 2008. There, the strength is proportional to the square of the electric dipole moment, which is measured in units of the dBi. Generally speaking, you can say that the magnetic dipole-dipole interaction relative to the electric dipole-dipole interaction is of a factor 10 to the minus 4 decreased, and this comes about because this ratio here is proportional to the square of the Sommerfeld fine structure constant, which is 1 over 137 approximately. However, for these heteronuclear molecules, one has to be aware that these ones turn out to be chemically unstable. So at present, several groups in the world are trying to really produce chemically stable heteronuclear molecules, which would then have a very large electric dipole-dipole moment, and one has still to reach quantum degeneracy, both for the bosonic and also for the fermionic parts. Now, when we talk about a harmonic trap, we might have a cylindrical symmetry with this trap aspect ratio. And concerning the interaction potential, we just have to take the sum of a contact interaction, which is short-ranged, whereas this dipole-dipole interaction is long-ranged in the sense that it falls off with 1 over the distance cubed. An additional difference between both interactions is that this contact interaction is isotropic, whereas the dipole-dipole interaction is inherently anisotropic in the sense that when you have two dipoles standing side by side, they repel, and if they sit on top of each other, they attract. And in between, if we have some angle theta, the angular dependence is given here by this term. So the interesting prospect of considering dipolar BCs is the following, that on the one hand, we may have a one-particle potential having a symmetry axis, and on the other hand, if we consider a polarized dipolar BEC, also the two-particle interaction has a symmetry axis, and you can easily imagine that both symmetry axes have a certain angle with respect to each other. So you would assume that then also the properties of the dipolar BCs depend on the angle between those two possible different symmetry axes. Now let me come first to the mean field picture, which has been elaborated some time ago by Claudia Eblein, Stefano Giovinazzi and others. The idea there is that we consider our condensate wave function, which is complex, and we may decompose it into a particle number density, condensate density and not, and also in terms of the phase. And the corresponding action then has this form, where in the Thomas Fermi limit, the energy here is just the trap potential plus the respective energy contributions from the contact interaction and the dipole-dipole interaction. In a very simple-minded variational approach, which turns even to be exact in the Thomas Fermi limit, one can perform a variational ansatz saying that the condensate density and the phase have just the dependence one would have without the dipolar interaction by introducing some Thomas Fermi radii and here some parameters alpha, plugging this variational ansatz into this Gross-Betayevsky action and optimizing with respect to these variational parameters finally leads to effective equations of motion which have a classical form with some mean field energy, and this mean field energy just decomposes into respective contributions coming from the harmonic trap, coming from the contact interaction, and finally also here coming from the dipole interaction, where epsilon dd is the relative strength of the dipole interaction with respect to the contact interaction. And this function f here is a so-called anisotropy function, which always appears when you deal with dipolar quantum gases, irrespective whether you deal with dipolar Fermi gases or whether you not deal with zero temperature physics but with finite temperature physics. It's just a function which varies between 1 and -2 and just has here the ratios of the Thomas Fermi radii Rx, Rz and Ry, Rz. Now, once you have such classical equations of motion for the Thomas Fermi radii, one would like to see what kind of static and dynamic solutions are possible. And one way to analyze this is to look for the aspect ratio for the equilibrium. And here is plotted the ratio of Rx over Rz. So the aspect ratio of the condensate versus the strength of the dipole-dipole interaction. And the main tendency is that increasing the dipolar interaction strength decreases the aspect ratio. And this is just the behavior shown here in this mean field cartoon. The condensate becomes elongated in the directions of the dipoles. That's the static case, and then one can also analyze the time of flight. And by analyzing the classical equations of motion, and here the main feature is that if you consider the case that the symmetry axis of the trap and the symmetry axis of the dipole interaction are parallel or perpendicular to each other, lead to different time of flight absorption results, where here the aspect ratio is plotted as a function of the time of flight. And this was the final proof that in the chromium BEC really the dipole-dipole interaction is present. Now the question arises, how does this picture change when one goes beyond this mean field Gross-Betayevsky picture? To this end, one has to look for the Bogoliubov-de Gennes equations, which one cannot solve for these dipolar systems. However, invoking the semi-classical and the local density approximation, which are valid in the thermodynamic limit, it turns out that the Bogoliubov-de Gennes equations can be analytically solved, and both the depletion and also the ground state energy are shifted due to the interactions. So the black terms here are always the respective terms you would have for a pure contact interaction, and the red and the blue term here are the dipolar enhancement factors. And you see that for the depletion of the condensate, the variation due to the dipolar interaction is between 1 and 1.3, whereas for the ground state energy, the dipolar enhancement can be even as large as 2.6. The idea now is to take this shift of the ground state energy coming from a Bogolubov-de Gennes theory and plugging this within a superfluid hydrodynamics as an additional energy into these equations of motion, which then allow to predict what happens to the Thomas Fermi radii once these quantum fluctuations are systematically taken into account. And by doing so, it is always assumed that these beyond mean field corrections are small perturbative corrections to this leading mean field behavior. And there are two results here shown. First of all, the aspect ratio changes due to the quantum fluctuations. Whatever we have here is positive. Positive means that the tendency to be elongated along the direction of the dipoles is reduced due to the quantum fluctuations, and depending on the concrete relative size of the dipolar interaction strength and the trap aspect ratio, one can have different results. So the idea is if one would go from the atomic magnetic dipole-dipole interactions to the molecular electric dipole-dipole interactions, then beyond mean field corrections have to be taken into account in a considerable way. Also, the time of flight results, where the trap aspect ratio is plotted as a function of time, change significantly once beyond mean field corrections are taken into account. So let's switch gears and go to the other topic. So we go back to pure contact interaction BCs. But now we consider the question, what happens if we switch on such a random distribution of mountains and valleys, a disorder potential. Such a disorder potential, how it is realized, I will tell in a second. Such a disorder potential is characterized by two quantities. The first quantity being the average height of the mountains or the average depth of the valleys. That's the strength of the disorder. And the second property is the average distance between two mountains and two valleys, and this is the so-called correlation length of the disorder. Now, if we switch off for a second the disorder potential, what can the bosons do? They go either in the macroscopic occupied ground state, or they go in some excited state. So the bosons have two possibilities. If we now switch on such a disorder potential, it turns out that the bosons may have a third possibility. Namely, they can Bose-Einstein condense in the respective minima of such a random potential. Which means when you deal with a disorder, then bosons have three possibilities. Either they macroscopically occupy the ground state, or they go in the excited states, or they contribute to local BC droplets which arise and emerge in the minima of such a random potential. Now, let's first of all motivate physically how such disorder potentials may arise. They can arise in a controlled way, for instance, by using laser speckles. There, the experimental setup is as follows. You have a laser shining through a glass plate, and glass is something diffusive. So behind the diffusive glass plate, one obtains an irregular interference pattern, which may be of a form which I have just shown as a random potential, and this is then reflected here to a BC cell. And what does one observe? This is from an experiment from the Ingusho group. One observes a fragmentation due to some strange reasons in the experiment. The strength of the disorder was measured in units of hertz, so 0 hertz means no disorder, and now the disorder is switched on, and here you see this fragmentation being due to the case that we have local BCs, so you have a loss for the condensate, and therefore this fragmentation here occurs. Now, we have made recently a proposal how isotropic laser speckles may be constructed when you have such a geometry the laser speckles are by construction anisotropic because you have a preference direction, which is just the direction here of the laser light. Our idea to maybe experimentally realize an isotropic laser speckle potential goes as follows. We have some ellipsoidal refractive cavity, some tiny holes here, shine some laser through it, and in the focal point A, we assume to have a glass sphere, which then distributes the laser light, and all laser lights here have always the same interference way to go until the focal point B, where we suppose to have a Bose-Einstein condensate. Now, there's also the way to get disorder undesiredly by so-called wire traps. So there have been experiments in the Tübingen group here of Fortouch-Zimmermann or the Schmidtmeyer group, formerly in Heidelberg. There the situation is as follows. You have a wire of, let's say, a width of 100 micrometer and a current through it, which gives you this magnetic field, the circular magnetic field. And if you add some homogeneous magnetic field, what you get at a distance of, let's say, 10 micrometer is you get a nicely harmonic potential. And this minimum of the harmonic potential is now measured once you go along the z direction. And this graph here shows that this minimum changes of the order of 10 to the minus 4 or 10 to the minus 5, which is a tiny irregularity, but nevertheless it is there and has to be dealt with. And this irregularity comes about because a wire is not a perfect cylinder. A wire has irregularities at the surface, and these irregularities at the surface translate themselves into irregularities of the current transport through the wire, and gives here rise to these curves. Now, this field of disorder is very intriguing because we know that the field of ultra-cold random gases lives from the pure control of one particle and two particle properties. So, but the real world is different. When we have condensed matter physics, we have all kinds of defects and dirt. So the idea is, with this field of dirty bosons, to fill the bridge between the perfect world of quantum gases and the dirty world of condensed matter physics. And it is called the dirty boson problem because there are so many parameters involved. The whole phase diagram is not known because you have so many parameters. But in some particular parameter ranges, one can say something. And there has been now 20 years ago developed a Bogoliubov theory for dirty bosons by Wang and Meng. And I would just like to go briefly through the results. For the most simple case that we have a homogeneous BEC, we have delta correlated disorder, which is experimentally not accessible, but a nice theoretical model. And the result here is that one has a condensate depletion. The first term here says that the condensate equals the particle number density. The next term is the usual depletion due to Bogoliubov due to the on-site interaction, contact interaction. So due to the repulsive interaction, particles are scattered into some excited states from the ground state. And this last term has a minus sign. It's also a loss. It's also a depletion, but it comes now from the disorder because all the particles participating in the tiny BEC droplets, they are a loss for the global condensate. One can also ask the question, how does the superfluid behave? The superfluid turns also to be depleted. So in order to get this result, you have to give your gas a boost. You ask the question, what is the percentage of the material going with the boost? That's the normal fluid. And what remains sitting, the complement here, that's just the superfluid. And it turns out in this Bogoliubov theory, all particles are superfluid despite of the condensate depletion. But if you switch on disorder, this is this piece here, there's also a depletion. And this depletion of the superfluid is larger than the depletion of the condensate by a factor of 4/3. The factor 403 I cannot explain, but that this superfluid depletion must be larger than the condensate depletion. One can have a heuristic argument, namely when the superfluid is coming and you have here all the local condensates, then the local condensates represent an obstacle for the fluid. So whatever is stuck in the minima cannot be superfluid, certainly. But due to the obstacle behavior of the tiny BC droplets, the superfluid depletion is increased. Now the question is, although this Bogoliubov theory of dirty bosons is now 20 years old, there has been no experiment to verify or falsify the theory. So we asked ourselves, what could be a good experimental detectable quantity for this? And we came up with the idea to look for the collective excitation. So we went through again this Bogoliubov theory of dirty bosons, looked for a general correlation, looked for the influence of the harmonic trap, and the result qualitatively is the following. If you look here for effects of the disorder on the collective excitation frequencies, you always get curves like this, where the disorder effect on the collective excitation frequencies decreases rapidly with a dimensionless correlation length. And this is, from our point of view, the explanation why in these old experiments from Ingusho, no disorder effect on the collective excitation frequencies was seen, although the disorder was switched on quite dramatically. Because in the experiment it turns out that this effective dimensionless correlation length is 7, so they were operating here roughly. So all effects were already gone off, decreased to 0, irrespective of the strength of the disorder. So our hope would be if one could realize the same experiment, but now with a smaller correlation length. In the old experiments, the correlation length was about 10 micron. If you could go, let's say, to 1 micron, which is just only a factor of 10, the effective correlation length instead of 7, you would have 0.7, and with this, you would have a detectable effect on the collective excitation frequency. So that's a suggestion which is already a little bit old, but somehow I cannot resist mentioning it again and again in order to hope that one day maybe some experimental group really does this experiment. Now, another effect is the following, that the condensation temperature is shifted. The condensation temperature shifts positively as a function of the correlation length because of the following. The condensation temperature for a BEC is always proportional to the density which you have in the center of the cloud. And whereas the interaction, contact interaction is always repulsive, so the density decreases in the center, therefore also the critical temperature decreases according to a very old result from Stringari and Pitievsky, 1996. When you have disorder, the situation is different because disorder on the average acts always attractive. Why? Because when you have here and here 2 places and you have a mountain in between, well, then nothing happens, the particles remain where they are. But if instead between the 2 places there is a minimum, well, the particles come together. So disorder has on the average always some attractive feature, which means in the trap effectively the particles go, so to speak, to the center if the effective correlation length is small enough, so the density increases and therefore the critical temperature increases. And strangely enough, we found a non-monotonic behavior with respect to the correlation length, because when the correlation length becomes larger, then basically the situation is inverted because more minima are outside of the region, so the particles flow then from the center to the outside, which leads then to a decrease here. Also, this prediction is still lacking some experimental verification. Now, what is the general picture? If you do not go to 0 temperature or to the critical temperature, what is roughly the picture for a general temperature? And we have looked for a Hartree-Fock mean field theory. And basically, there is a new phase which emerges apart from the usual gas phase and the usual superfluid phase. There's also a new phase emerging, the so-called Bose-Glass phase. And this Bose-Glass phase means there is no off-diagonal long-range order, no condensate, but still we have the local BC droplets. Now, if the Bose-Glass is really a new phase in the sense of critical phenomena, what you would like to have is an order parameter. When this is non-zero, it characterizes the presence of the Bose-Glass. And to this end, we looked in the literature and transferred the so-called Edwards-Anderson order parameter from the theory of spin glasses to the Bose context. And this is the small q here. So the idea is, if you look for psi star correlations and take the quantum average, which are the brackets, and take then the disorder average, you have off-diagonal long-range order giving you the condensate density. But if you take the psi star correlation, take first the quantum average and then square and take the disorder average, then you get not only a contribution from the condensate density, but in addition also from this Edwards-Anderson-like order parameter, which indicates the Bose-Glass. And to make a long story short, the qualitative picture for the phase diagram looks like this for delta-like correlation, disorder correlation. So here is the strength of the disorder, here's the temperature. If the disorder strength is small enough, you still have the usual case that the gas goes into a superfluid. But if the disorder strength becomes large enough beyond this tri-critical value RC, then the gas first goes in the Bose-Glass, which means first we have the local droplets, and only when the temperature is then lowered further, one gets the superfluid phase, where, at least according to our Hartree-Fock result, not only a global condensate, but also these tiny droplets coexist. So far for this overview about the dirty boson problem. And now I would like to bring both topics together. So I would like to ask the question, what might happen if we bring a dipolar BEC in such a random landscape? Now, the idea basically is first the following. If we just consider a dipolar BEC, at zero temperature, Bogolyubov says everything is superfluid. And only when you introduce thermal fluctuation, it turns out that breaking the isotropy due to the dipolar interaction leads to an anisotropic effect of the superfluidity. It does now matter for at finite temperature whether the particles are moved along the dipoles or perpendicular to the dipoles. That's an effect of finite temperature. However, if you go to zero temperature, despite the dipolar interaction, superfluidity is isotropic. But if we switch on a disorder potential, it turns out that on the average, on the disorder average, superfluidity turns out to be anisotropic. So we went in the general case through this Huang-Meng theory, where we have a general interaction potential, a general disorder correlation. So there's a general expression in lead for small disorder, general expression for the condensate depletion, and also for the superfluid depletion. And the superfluid density becomes, as the superfluidity is a response quantity, becomes a tensor, which means it matters whether you try to move the condensate parallel or perpendicular to the condensate. It becomes a tensor. And only if you have isotropic disorder and isotropic interaction, one gets back the good old result from Huang and Meng. Now, if we specialize to the concrete case we would like to discuss, namely here two dipoles polarize along the z direction, and we have also our relative interaction strength, epsilon dd as usual, and Gaussian correlated disorder, we get following result. The condensate depletion is now, apart from the usual Huang-Meng term, gets an additional factor, which depends on the relative dipolar strength and also on the disorder correlation. And now, unfortunately, the disorder correlation is no longer psi as previously, but now it's called sigma. And here we see that what is always the case, when the correlation length is increased, the effect of the disorder decreases, and this depletion increases with increasing interaction strength. Now, if we go to the superfluid depletion, the superfluidity becomes this tensor having a perpendicular and a parallel component. The perpendicular depletion has qualitatively a similar feature as the condensate depletion, namely it increases with increasing dipolar interaction strength. But strangely enough, for the parallel component, we found the result that with increasing dipolar interaction strength, the depletion decreases, which is counterintuitive. Here it increases, here also increases, but here it decreases, which is at first counterintuitive, because there is a critical point, a critical epsilon, and here even a critical line as a function of the correlation length, where the superfluid depletion becomes smaller than the condensate depletion. Remember, previously in the Huang-Meng theory, I have argued in favor of the factor 4/3 that the superfluid depletion must always be larger because the superfluid flow is hindered by the local BECs, but here it's opposite if we consider a flow parallel to the dipoles. And we interpret this strange finding as follows, that I have told you so far only half of the story. I assumed always when the bosons are in the local minima, they remain there forever. But that's not true, because the picture is more dynamic. The bosons go into the local BEC, remain there for a certain localization time, and afterwards they go out and other particles go in. So we have to adopt to the concept that the local BECs exist on the time average, but the bosons participating in the local BECs go in, and after some localization time they go out, and this heuristic finding of a finite localization time was supported by some other calculations we have done in 2009. Now, you can ask the question when you perform a hydrodynamic theory on top of this, what you get. And to make a long story short, the result is that if you have a dipolar BEC in a random landscape, the sound velocity becomes very particularly angle dependent. So it matters in which direction you send off your sound wave, the sound velocity becomes different and can be analyzed in detail. And this would be certainly a very interesting quantity to look at. And I'm optimistic that, for instance, with Bragg spectroscopy, such anisotropies of the sound velocity could be detected. With this, I come already to the conclusion. Concerning dipolar Bose-Einstein condensates, it might certainly be interesting to generalize the zero temperature findings where only quantum fluctuations were dealt with here, also to finite temperatures, and to look for the competitions between quantum and thermal fluctuations. Concerning the dirty boson problem, we have seen that the bosons can be in the global condensate thermally excited, and as a third and new possibility, we may have local condensates in the respective minima of the random potential, and the whole phase diagram, even for strong disorder, is still not known, so further work has to be done in that direction. Concerning the anisotropic superfluidity, this emerges due to a delicate interplay between the isotropic disorder and the dipolar interaction, and we have not yet looked at the consequences for trapped Bose-Einstein condensates, so this is certainly also interesting topic to look at. And finally, the standard two-fluid model, which is used all over in our field, certainly needs to be generalized to a three-fluid model, because the local condensates represent, so to speak, an independent fluid component which is stuck, so its velocity is zero, but nevertheless some particles go there and they would have to be incorporated within a three-fluid model. And with this, I would like to thank the bold-faced people here have contributed significantly to the talk. For instance, with Aristeo Lima, a former PhD student, we worked on the dipolar BECs. The disorder topic was generously funded by Volkswagen and DID. And last but not least, I would like to advertise and announce 2 quantum gas events which take place consecutively in August this year. First of all, there will be a school on low-dimensional quantum many-body systems, in particular dealing with the Tongshiro gas, the Kosterlitz-Howlett phase transition, and also laser speckles, Anderson localization. This is organized within the Collaborative Research Center as FBTR 49. And afterwards, we will have a Wilhelm Else and Herreo seminar on general topics of quantum gases with the title Quo Vadis BEC. And I would be very glad if some of you, we can see us again. If you want to apply for both events, please look at my homepage. And with this, I thank you for your attention.